first topic in the electronics course, and it will be about operational amplifier. Today we'll start to look at the characteristics of the ideal amplifier, the methods to analyze circuits with Opamp, and also later, inshallah, we'll try to look at methods to design circuits with Opamp. Maybe we'll have one or two examples today, but we'll continue on that later. Then we look at different applications for Opamps, why we are interested in the Opamp and how it is useful. And then we'll look at some non-ideal characteristics. So at the end of this chapter, you should be able to know the Opamp itself, the ideal characteristic of the Opamp, how you can deal with that, the non-ideal characteristic of the Opamp, and how to analyze and design circuits, including Opamp. And of course, our chapter here is chapter 2 from your textbook, so you can look at that for your reference. So let's talk about the Opamp, and for short, it stands for from operation and amplifier. Okay. So in short, we'll just call it Opamp all the way. We have this device. It's actually 5 terminals device. So we have the inputs to be non-inverting, which is this one here. So this is the non-inverting terminal. This is non-inverting pin. This one is the inverting pin. So these are inputs. Okay. It should be obvious that you have your input from this side, not the other side, right? And then you have the output taken from 3 of the 7 forward result, of course, but this is the V output pin. And then we have 2 power supplies. We have plus 15 and minus 15. At the end of the day, this is an active IC, an active chip. What I mean by active chip? What is the difference between active and passive element? You have an active element and passive element. I want you to differentiate between active element and passive element. What is the difference? The power, exactly. And this is obvious. Any active element should have a power supply. To be power, to be operational, okay? And then you can operate the circuit accordingly. But the passives, actually we have the resistor, caps, inductors. These are passive elements, okay? So these are the terminals of the Opamp. We usually ignore these terminals. I mean, sometimes we just draw the Opamp as this. So maybe plus, minus, and the output. Okay, we usually exclude the pins of the power supplies. But it does not mean that you can operate the Opamp without power supply. No, you should operate the Opamp with power supply. If you have your kit off, the Opamp will not work. What's the why do you? We'll come to that. We have applications for this, and we'll come to that later, inshallah, how we amplify signals and so on and so forth. But we have many applications for the Opamp. It's not only amplifier. That's fine. That's fine. Well, we are going through this, inshallah, throughout the topic. So at the end of the day, you need sometimes, if we analyze the signal, process the signals, for example, the sound signal, they may be weak, okay? Their amplitude may be in millivolts, so you want to amplify that to volts, so you can process them. And that's why we need an amplifier. عشان تعمل amplify the signal, weak signals. This is one application. Another application can be a filter. You can use the Opamp to do a filter or to implement filter. You can do differentiator, integrator, whatever. And you'll study that more in implementation in the lab, inshallah, if you take the 272. Okay. So this is the symbol of the Opamp, and these are the terminals. We have inverting input, non-inverting input. We have output, we have power supply, positive and negative. And as I mentioned, Shabab, usually we just exclude the power supply terminals from the symbol, just to simplify things. Okay? But at the end of the day, you should be able to know, you should know that the Opamp cannot operate without power supply. Okay, then what is the operation of the Opamp? What is the function of the Opamp? Actually, it takes the input. It amplifies the difference of the input. It amplifies the difference of the input. So the output actually should be something like this. V out will be some gain, and we call that gain differential gain because now we are taking the difference. Okay, So let me maybe take put in some space here. So this is V out. We have some differential gain, and then it amplifies what? The difference. V negative is V positive minus V negative. So if you have two inputs here, okay, if you call it this one V1 and V2, this one can be V2 minus V1, right? Okay, so this one can be V2 minus V1, the non-inverting minus the inverting. And then this is the main feature. We need the op-amp to operate like this. We need it to take the difference and amplify the difference. واضح؟ تاخذ الديفرنس وتعمل له ايش؟ amplification. But there is non-ideal, or there is another thing it does that we don't want to have it in the function, and it is the common mode part. So this is common mode, and from the name it is what? V positive plus V negative, but now over 2. Okay? But usually we just ignore that term. We ignore this term, the common mode. We usually study it more in 303, not 203. Okay, so we keep it simple here in 203, just to focus on the main contribution or the main function of the op-amp. ايش قلنا المين function حق الop-amp؟ difference. Amplify the difference. هذه كلمتين مهمة جدا. Amplify difference. Okay, مهم جدا. It cannot amplify the summation. تمام؟ مهم جدا الop-amp نعمل يا شباب amplify the difference. الترم اللي بعد هذا الثاني الكومن مود, it's something we don't want. It is undesired. We want to take it off, but it is there because of some other non-idealities. We just implement this one. I mean, work on this one in 303 more. Okay, so this is what we need from the op-amp. So it amplifies the difference. It takes. It also amplifies the common mode that's undesired, but we have it anyway. But in our analysis, we usually take it out. Okay, so how can we use the op-amp? The op-amp can be used in 2 configurations. It is either an open loop, it means there is no connection from the output to the input. Okay, there is no connection from the output to the input, or it can be an open loop. It means there is. Sorry, did I say that? Yes, I said the open loop. There is no connection from the output to the input. Okay. But if it is in closed loop, there is a connection from the output to the input, and we will deal with both. So let's take one example of the. Okay. So before doing that, let's just go deep and see the features of the op-amp itself. The first feature of the op-amp, from the inputs, you can imagine you have an infinite input resistance. An infinite input resistance. So the resistance seen from the negative to the positive terminal, it is infinity. What does that mean? Do we have the current flowing? No, there is no current flowing. So the current flowing into these 2 terminals should be 0. So this is what? This is infinite. So the current of I negative equals the current of I positive equals to 0. No? By the way, this is ideal characteristic. It's not the real characteristic. There is an impedance, but it is high impedance. So we can imagine that it is almost 0. It just simplifies our analysis. So this is the first feature, the infinite input impedance. الأوضاع يا شباب بيكون عنده infinite input impedance. And we can just make it here general impedance and the resistance, capacitance, but it is actually resistance. And that will result in the I negative equals I positive equal to 0, which will simplify the analysis very, very, it will be very clear in our analysis later, inshallah. The second thing, we can say we have very large gain, differential gain. احنا قبل شوي قلنا ايش؟ differential gain عبارة عن ايش يا شباب؟ الفانكشن عبارة عن, so this is V out, differential gain, V positive minus V negative, right? It amplifies this difference. So now the differential gain will be very, very, very large, okay? And it can be infinite. We can assume this one to be infinite. By the way, the usual 741, it has about 100,000. of gain amplification, which is 1,000 per volt. Okay, 100,000. Does it mean that if you apply 1 volt, you will get 100,000 volts? No power. If you can just take the Opamp, if you take the Opamp, this is, let me make this one V positive, and the other one is V negative. Okay. And you connect this one to 0, you connect this one to maybe 1 volt. And then I ask you, Shabab, if this is your AD equals 100K, of course, volts per volt, because this is voltage gain, 100K volts per volt. And by the way, this is a real number. Your 741 is the whole cheapest and wide used Opamp. It has that amount of gain. It can be higher. So in that case, can I say I will see 100K volts at the output? Would that be the IC? You cannot, right? What will it say? What will it say, Shabab? Exactly, which is, or which are the power supplies. So you have power supplies here, and usually the power supplies can be connected for 741. For example, 15 volts minus 15 volts. So if this is your circuit, what you are expecting? 15 maximum. It cannot go beyond the 15, right? This is the maximum. And أنا بعطيك ما بعطيك ما بتاخذ شيء أكثر مما أعطيك, right? You cannot get more voltage. From where you get that much voltage, right? There is no way. So it will be saturated to 15 volts. So if you have 1 and 0, this one is expected. If I give you this simple circuit, you should be able, okay, this is 15 volts. The output is 15. How about if I exchange the terminals negative? Right? Keep it easy, keep it simple. هذا قاعدة دائما لازم تعرف وش وتقتنع فيها. Okay? So that's minus 15 exactly. It cannot be 100K.
What is the rule for 100?
Which one? You mean the differential?
Yes. So we use it from what, or we.
From where we get this number?
Yes, or we use it to get what or to know what.
This is the function. احنا الآن نستخدم الفانكشن. This function, you will use this function to analyze the circuit later. تمام? So we'll use it. But first we'll start with the ideal case. The ideal case, AD is infinite. There is no AD. If your AD is infinite, okay, let me maybe put it here so it can be also recorded. If this is the case, I'm not sure if I have space. Yes, okay. So if this is the case, we have V out equals AD V positive minus V negative, right? Now, can I say V out over AD equals V positive minus V negative? Is that right? Okay. So by saying very high or infinite open loop gain, this is, we call it open loop gain because the output is not connected to the input by any resistor or any components. There is no connection, there is no closed loop. Closed loop معناته الشباب the output, there is some connection between the output and the input. We'll come to that. So if this is the case, this is what we call open loop gain. إذا كان الopen loop gain اللي هو AD infinite, what will be the equation? Can I say this one 0 equal V positive minus V negative? طبعا if AD goes to infinity. That's correct. And then we have a very important result saying that your V positive actually tracking V negative. Okay, it's trying to track V negative. And this is correct when you have what? When you have actually, in this case, this is an ideal case, but also in closed loop configuration, if you have a negative feedback. If you have negative feedback, the positive terminal or the non-inverting terminal is trying to track the inverting terminal. Although they have different voltages, right? V positive, V negative. But if they are connected in closed loop and negative, if they are connected in closed loop and negative, the non-inverting will track the inverting. And this is very important feature. We'll analyze the circuit very easily, inshallah. Okay? The third one, it has a zero output impedance. Okay, and I have a space, no space. Okay. Yeah, maybe I need to erase this one. Okay, so it has a zero output impedance. Usually, if you model the amplifier should be modeled something like this. So you have a positive terminal, negative terminal. That's your R input, right? This is our R input, and our R input is what? Infinite, but we'll keep it there. Then you have a voltage control, voltage source here. That will give you the amplification. So this is AD multiplied by, maybe let's call this one V positive, and this is V negative. So this one will be V positive minus V negative. Okay, so you will have some voltage, that voltage actually following the function, this function. And then there is a little non-ideal component here that we don't want to have, which is our out. نحن شباب أفضل حالات الامplifier, if it is voltage amplifier, should we have the R out here or we need to make it zero? إذا كان عندك الأوتبوت voltage هنا, this is your voltage and this is your output voltage. أنا أبغى الفولتج اللي هنا يطلع كله بالأوتبوت. If this is the case, what is the best value of R out? Zero. أنا أبغاها zero. So ideally, I need to push my R out to be zero. Then there is like a line connected between this voltage, which is, let me call it Vx and Vout. And this is the case in ideal Opamp. And most of the time, Opamp has very, very small output impedance. It is about 50 ohms or so. Okay. So this is the third ideal characteristic. So we just deal with the RO to be infinite, sorry, zero. And of course, this is for voltage amplifier. If it is current amplifier, it should be exactly the opposite. The RO should be infinite because you want to take the the current, all the current out. And of course, you don't have that. You have a parallel connection of RO. We'll come to that inshallah. Now, also what we have the zero common mode gain, which is the ACM. We talked about this one. We just ignore it, right? We just ignore it and use this one. And then it means the common mode rejection ratio is infinite. What we mean by common mode rejection ratio, if you have two signals, they have noise between them. You want to take the noise completely. Okay? To do that, you want to have the common mode equal to zero. لأنهم common, a noise common between two signals, صح? You don't want to amplify the noise. You want to amplify the difference, but not the noise. And to do that, you have your ACM equal to zero. And the bandwidth. Do you know the bandwidth? What is the bandwidth of any circuit? Limitation of frequency. Exactly. It says. So the bandwidth is actually related to the frequency of the circuit. It means the speed of the circuit. It means the frequency it can process. Can I process 1 megahertz signal? Can I process 1 gigahertz signal? Can I process 10 gigahertz signal? And so on and so forth. If you have infinite bandwidth, it can amplify any frequency from 0, which is DC, until terahertz, right? And this is the case with ideal amplifier. So in ideal op amps, we assume there is infinite bandwidth. It's not the case in 303. In 303, we'll go deep and study the bandwidth limitations. But here we'll ignore the bandwidth completely of the course. Okay? But in 303, we'll study that inshallah in detail. But you need to make sure, you need to know that the op amp cannot go beyond some certain limit. For example, 741, the limit is 1 megahertz. Okay, you cannot process 10 megahertz or 10 gigahertz and so on and so forth. Okay? I mean, you can process them, but it will be attenuated. And if you apply 1 volt, expecting that you have 10 volts, you will see what? 0.1 volt. It's just going down, it's opposite, not amplification, it's actually attenuation. Okay? So again, this is the ideal number. عندنا قلنا يا شباب infinite صح؟ الار انبوت راحت. أو الرسمة راحت. معلش. الرسمة راحت الحين. تخيلوا معي الرسمة من جديد. Let me put it here again. So that's the ideal, that's the let me say the model. Okay. So this is AD, V positive minus V negative, R out, R in. Right? All of this inside your Opamp. You don't see that, by the way. This is a model. And by the way, the Opamp has maybe around 20 to maybe 30 or even 50 transistors inside. but you don't see that. You see only, I mean, you can model that, like a behavioral model. So the ideal of them will say that this is infinite. It's not there, right? And this is the case. This is infinite. And the result of that the entering currents are zeros. Okay? Then the output impedance is what? Our out is what? Zero, exactly. That is a wire. There is a connection between your voltage coming in this way here and the output voltage right away. Okay? And of course, maybe this one is grounded, so okay, you can finish that as well. Okay, so we'll take this one out, as we said. The common mode will take it out from the equation. And yes, so can we use, we talked about this one, using the Opamp as an amplifier in open loop configuration. We said yes, it can amplify the difference, but the problem, it will saturate. We need to make sure. لأن ال AD يا شباب, even if you have 0.1, تخيلوا معي في difference between ال V input and V negative of 0.1. 0.1 multiplied by 100K, it's 10K, right? 10K, can you get 10 kilovolts? We cannot. So usually we don't use the amplifier in open loop, configuration. We use it in closed loop. We'll study it more. Okay? Unless you have a very, very, very tiny difference between them. Okay? And this is not practical as well, because we have some other what we call offset voltage. And imagine you have some microvolts difference between them. Okay, and even in microvolts, yeah, there is some voltage you can see. But yeah, it's not that practical. So usually we use what we call instrumentation amplifier. This will come later, inshallah. I'm trying to link things together somehow. But anyway, we usually use the closed loop, open loop configuration like this to compare. تخيلوا معي يا شباب، إذا كان النيجاتيف أعلى من البوزيتيف صارت عندك minus 15. إذا كان البوزيتيف غيرنا خلينا هذه بوزيتيف negative and positive. If positive now is higher, now it will be plus 15. So you now have two states, either plus 15 volts or minus 15 volts. Can we say this is nothing but a comparator? So we are comparing two signals. Which one is higher, sir? You are comparing. And this is a very nice circuit. We call it comparator. And I'll give an example for the comparator. For example, if you have, let me say, this is your maybe negative connected to ground. Your positive is connected to off. Do it the other way around. So let me connect this one to a voltage source. Okay, and that voltage source is, it has what? It has 1 volt, let's say, and that 1 volt is actually like if you are having a temperature of 25 centigrades. Okay, imagine that. So this is the threshold voltage. If you have a temperature, then of course there is a circuit here. But imagine that circuit will give you a voltage source that gives you 1 volt for 25 centigrade of degrees. If you have a temperature sensor here, so you connect this one to what? A temperature sensor. Okay, so this is minus plus. And then your temperature sensor is actually going up and down between, let's say, 0.5 until 1.5. So 0.5 volt until 1.5 volts. So it goes up and down, okay? Or maybe changing from, let's say, 0 up to 1.5 volt. That's also fine. This is 1.5 volt. This is the time. Okay? And then you are connecting this one. Of course, you need to connect this one to a relay. But let's imagine you are connecting this one to a fan, small fan. Okay? We usually don't do that. We need to have relays and so on and so forth because you don't have that much of power.
X-axis is time or the temperature.
Right. But you have a voltage that is changing with the temperature. You can imagine that as a temperature as well. That's fine. But let's keep it simple. It's time. So now, if this is the case, what is the threshold voltage? And this is your output. So this is your input of the temperature sensor. And this is your threshold voltage. Right? This is what? 1 volt. Exactly 1 volt. Right? And this is going all the way up to 1.5 volts. And this is the output. So this is the output. Let's now try to imagine the circuit. So this is the point where the V negative, V positive becomes higher than the V negative. In the case of having the V negative higher than the V positive, what will be the V out? Negative what? Negative 15, right? Or negative power supply. Let me call it negative VEE. Let's call this one VCC, and this is VE. It will be clear, inshallah, later why we call it E and C later. So this is what? V negative, because the V negative terminal is higher than the V positive terminal. Once the V positive becomes higher than the V negative, what will happen? This one will switch to VCC. So this one will go all the way to VCC. And imagine that the fan will turn on here. So the fan will turn on once you have the high temperature. So the fan can be on in this case. Okay? And this is a very simple circuit for the comparator. You can always compare things together. Okay? Any questions? Okay. Let me now go to the closed loop configuration. Of course, now the comparator will close the comparator section. Now you should be able to know the comparator function. It is comparing two signals, but with very large gain. It means it either goes to plus 15 or plus VCC and or minus VCC. Tamam? طبعا of that يا شباب, the negative terminal can be connected, power supply can be connected to 0. So sometimes you connect this one to 0 and plus 15. So this one should go from where? 0 to 15. Okay. So let's do now the closed loop configuration. We have two configurations. It can be either non-inverting or inverting. So the output can be, the phase of the output can be in phase with the input or out of phase of the input. And by the way, we are studying here negative feedback. Negative feedback closed loop configuration. We are not studying positive feedback. You will study positive feedback later in filtration. Okay, so let's start with the inverting amplifier. And we need to analyze the circuit. Where is the space? So start from here. Okay, what do we know about the Opamp? What is the feature of the Opamp if it is idle Opamp? قلنا نقطتين جدا مهمة, right? The currents, those currents entering the Opamp are zeros and infinite gain. If it is infinite gain, it means your V positive equals V negative. So you should start with this one. This is in your mind. So always, shabab, you have this one. So V, let me start with the currents. I like to start with the currents. So I positive or I negative equals to I positive equals to 0. Okay, so keep this in mind. And it doesn't harm that you just write it every time. That's fine. Just keep it in mind. And then also we know that V positive equals V negative. Okay, too, because AD is infinite. Okay, you should have that assumption, and that you need to know what you are doing. Okay, you just don't like numbers or equations blindly. You need to know what you are doing. Yes,
We always deal with the ideal.
Yes, and sometimes if you ask you, it's not ideal. We'll let you know that the case, and then you cannot say this. The second condition is not valid. By the way, the first condition is almost valid. Almost, yeah? Almost always. So there is an infinite impedance. Finite input impedance, but usually it is very large input impedance. So we just the first condition is always valid. Okay. With some reservation sometimes, but this is always valid. Okay. So now what is next? What is the transfer function? Now we want to analyze the transfer function. You remember your refresh quiz, right? What is the transfer function? Exactly, V output over V input. So if this is your V output over V input, this is what we want to find. We want to find V output over V input. Is what? It's an expression. You need to find that. Have a space here. So let's start with this one. So if you know this, the current is going to be 0. So I equal to 0. Another I equal to 0. Can I apply KCL here? Yes. And by the way, we don't, keep in mind, we don't apply KCL at the output terminal. Do not apply KCL at the output terminal unless you know the current going in or out of the op-amp, because we don't know anything about the current going in or out of the op-amp. Okay, so we usually ignore or avoid using the KCL at the output. If you know that current, then yes, go and apply. But if you don't know it, don't apply the KCL because it will be a disaster for your analysis. It will complicate things. Okay, and you'll not get much out of your analysis. So we'll start with doing KCL at V negative. So KCL at V negative node. And we know what is the voltage at V negative node? Because of the second equation, what is the voltage? V negative equals to 0. So V negative here, actually V positive equals V negative equals to 0 in this case. Applying your second equation. And now, if this is the case, I'm applying KCL. I'm saying, okay, assuming the current is flowing out in all directions, that's fine, just an assumption. So I'm starting with saying 0 minus, so 0 minus VI over R1, right? Plus 0 minus, so 0 minus V output over R2. Agree with that? And now you can have V output over R2 in one side, VI over R1 in another side. You can do that. So we have VI negative, of course, over R1 equals V out over R2. And what is the transfer function here? What is the transfer function we're looking for? V output over V input. So sometimes we call it VI, sometimes V in, I in, that's fine. Equals what? Negative R2 over R1. And this is the equation of inverting amplifier. Okay? So if you know R2 and R1, you can find the gain. This is gain of the circuit. Huh? For example, if R2 is 1 kilo ohm, sorry, R1 is 0.1 kilo ohm. What is the gain of the circuit? 1 over 0.1. What is the gain of the circuit? 10. Exactly. If your V input is 1 volt, the output is expected to be 10 volts. Exactly. So if your V input is 5 volts, the output is expected to be 50 volts. Do we have 50 volts? مين اللي حدنا؟ Exactly. 15. مهم جدا يا شباب. وهذه تربط الامور مع بعض. If you have an output voltage that exceeding your power supply, the Opamp will not give you that much, that revenue. It cannot, simply it cannot. ما عندي ما أعطيك يعني ما أعطيك volts من وين أجيب لك volt. Okay? So keep this in mind. By the way, شباب, after finishing every topic, I usually give you the slides, the annotated slide. But it's not discouraging you from taking notes, because I see some of you take pictures. That's fine, but I need you guys to take notes while you're in the class. And also another kind of resources you're recording with you. Another third of resource is what your annotated slide. So you can use all of it. Okay, let's do this design problem. Design an inverting Opamp-based amplifier. This is Opamp-based amplifier. So we are expected to have something like this. Plus, maybe plus, minus. Your plus is connected to what? To ground. Okay? You are connecting the input to the non-inverting amplifier. But in the second case, where you have a non-inverting amplifier, your input should be connected to the positive terminal. And then you have a resistor here. You have an input voltage here. Okay? And then you have what? Another resistor here, because this is closed loop and negative feedback, right? It is connected to the negative. And you can see that also as well from here. It is very obvious that you have a negative relation. Okay, so this is R2 and this is R1. What is the equation we are expecting? The transfer function? The out over V input equals minus R2 over R1. And now we just need to design. ايش معنى design يا شباب؟ Exactly. Finding values. Design, it means finding values. And after drawing, you need to draw, you need to know the system, and then what? If the system is not known, you need to analyze the system, and then finding the function. But we already analyzed the circuit, we know it. Okay, so what is R2 now? What is the input resistance? It says what, by the way? It says, I mean, the requirements, closed loop gain, which is this one here, because it is closed loop gain. It is not the open loop gain, which is AD. So this is closed loop gain. So the closed loop gain is 20 dB. What does it mean, 20 dB? It is decibel, but how can we change the decibel to normal scale? Okay, how we do that? 20 log. So the gain actually, the gain which is in voltage, it should be 20 log V out over Vn, right? And then if you have a 20 dB, how much of gain scale, normal scale, volt per volt? If this is 20 and this is 20, this will cancel each other, right? Yes. And 1 equals to the log, how much of that? The log is with the base of 10, right? So this one should be 10, exactly. This one should be 10 to give you 1. Log of 10 is 1. And then you should give 20 dB, it should give you 20 dB. Now let me ask you, what is the 40 dB normal scale compared to normal scale? If it is 40 dB, I give you a gain, I need a gain of 40 dB. The normal scale, which is volt per volt, how much of that? 100, exactly, about 60 dB. 1,000. This is logarithmic. You are doing with the multiplication of 10, right? How about 80 dB? Let us do 80 dB. 10,000. Multiply by 10. Right? So you need Shabab to somehow to get some feeling of the dB and the scale, and why you are interested in dB. By the way, ليش نعقد حياتنا؟ normal scale خلاص.
يكون ما يكون الفرق الشاسع في الارقام.
جميل. هو كلام سليم. هو اذا كان عندك فرق شاسع في الارقام انت ودك تتعامل معها بارقام صغيره. Okay, that's the point. So you want to compress that kind of thing. So now you are going from 0 to maybe 1 million, and in dB you are going from how much? Then 0 or 20 dB, let's say 20 dB until 120 dB. 120. So 120 dB is actually to power 6, because each 20 dB will give you power of 1. 20 is 1, 40 is 2, 60 is 3, 3 to power 3, and so on. Okay. How about 10 dB? If the kind of 20 dB, I take 10 volts per volts. How much of 10 dB will give you? Square root of 10. Right. Okay. So you can just take this stuff together, but it's not half, right? It's not half. That's the point. When I say 10 dB, it doesn't give 5 scale of 5, and it give you 5 volts per volt. So keep that in mind. Okay. So 20 dB in this case, in this scenario, 20 dB is actually nothing but 10 volts per volt in our normal scale. So what we need to do, we need to design our circuit to have 10 volts per volt. If your input impedance, what is the input resistance here, which is the one in the input side, because this is almost ground, right? If this is almost ground, you can see only R1. Imagine, Shabab, this is virtual ground. Can I say this? This is virtual ground, so can you see this? Because V positive equals V negative. And then you can see only this input impedance or input resistance. So what is, maybe if it is confusing, we just take this one as R1. If R1 equal 100K, how much of R2 to just give you that much of gain? R2 should be? Equation. Okay. If this is 100K, this is 100K here, and you need this one to be 10. Is it 1 over 10? Or you just multiply by 10? You just multiply by 10, right? So this one should be? Huh? resistance cannot be negative in passive, right? And we do have negative impedance. We do have negative impedance, but it should be active impedance. We don't do that here. But passive impedance cannot be negative, okay? Because resistance usually consume power. If it is negative resistance, should then give you power, supply power. It cannot give power without supply. So this one should be 1 mega. 1 mega ohms, right? 1 mega ohms to give you that much of. Is it clear, Shabab? This is very, very simple equation. It's a very simple design problem. Just give you some kind of walking movements. Right, let's do this practice problem before we go to the non-inverting amplifier. It needs some work here, but let's do it. Do we have a space? Perfect. So let's start from here. I will do it very quickly. So KCL, what is this one, Shabab? Virtual ground, right? Ideal zero. Ideal op-amp. So if ideal op-amp, it means AD equals or approach to infinity. It means V negative equals V positive equals to 0. Okay? And we know the current, the input current should be 0. Then I apply KCL at V negative node. If you do that, what will be the KCL here? So you have minus VI over R1. I don't want to write 0. It should be obvious, 0 minus, right? 0 minus V1. And then also you do have 0 minus Vx. Let's do Vx over R2 equal to or equals to 0. Okay, so what is Vx in terms of Vi? It can be what? It can be R2 over R1 multiplied by Vi. Right? And we are interested in the transfer function. If you are interested in the transfer function, we want to find the equation for what? V output over V input. So our goal actually is V out over V input. This is our goal. Keep that in mind. So at the end of the day, I want to exclude the Vx. I don't want to see a Vx in the equation, and that's why we are trying to find Vx in terms of Vi. Now let's do another KCL. Can I apply KCL here? The output. We can, but we don't want to do that. We usually avoid to do that because we don't know the current coming in or out the op-amp. Okay, keep that in mind. So then we have another node, which is X. Can I apply KCL there? Yes. So then we apply KCL. Let me do it in the other slide. So KCL at X node, and how much is that? What is the expression? So this is Vx over R2. Of course, the current flowing this way. This is connected to ground. So this is virtual ground, right? And then plus Vx, the current flowing here, it's what? R3 plus Vx minus what? V out over R4. Can I find Vx in terms of V out? So I put Vx here, one factor, 1 over R2 plus 1 over R3 plus 1 over R4 equals V out over R4. And we do have another equation for V input. I can take the V input and put it there. So V input or Vx I can substitute with the the previous equation. It is what? R2 over R1. So this is minus R2 over R1 multiplied by Vi multiplied by the rest. R3, R4, and then equals V out over R4. I think it's obvious now. You can relate V output to V input, right? You can do that yourself, but it should give you one. You can write the final equation. So the V out equals, you can help me, Shabab, here. So this is R4 here. You multiply R4 here. You put Vi, you divide Vi by V out, right? As if you are doing it in the other side, but I'm just kind of putting the sides logic here. So this one will stay the same. So we have minus, and let's multiply this one. So this one will be R2 minus, of course, R4 over R1, right? And then we have what? R2, R4 over R3 plus R2 over R1. Exactly. And by the way, you should be able, Shabab, to know if you are doing things right or wrong. Because if you have anything not dimensionless, these are dimensional. Resistance over resistance, voltage over voltage, two resistance over one resistor. We do have a problem here, right? What is the problem here? We do have a problem here. It is this is ohm, not dimensionless. We are missing one parameter, which is what? R2 multiplied by R4, R1, exactly. So just usually examine your expression. If it makes sense to you, now you are doing fine. If it is not following your units, it means there is a problem. Okay? Oh, yeah, R2. Okay? And there is a design associated with this. I will leave it to you. This comes back to me later. You have a gain of 100 volts, and you have an input impedance. Let's say, Shabab, it is R1. And let's keep R1 to be 100K for simplicity. So let's keep R1 to be 100K and this one to be 10 megs. So then you have a room to maneuver here. Okay. So if you have these values, try to put it there, and let's see if you can get the results right. Okay, we'll stop here, inshallah, next time.